let's go over the answers for this homework assignment. This first video is going to be just for the multiple choice. So we've got the first one. A rocket's continuously firing its engines as it accelerates away from the Earth. So here's something that's important. It accelerates away from the Earth, which means that the speed's increasing. For the first kilometer of its ascent, the mass of fuel ejected is small compared to the mass of the rocket. What that means is that the mass is basically staying the same. For this distance, which of the following indicates the changes, if any, of the kinetic energy of the rocket, the GPE of the rocket, Earth rocket system, and the mechanical energy of the Earth rocket system? So we talked about accelerating, which means that the speed is increasing. So that means that the kinetic energy has to be increasing. So if I look at rocket kinetic energy, A, B, and C are increasing, D is decreasing, so it can't be D. All right, the gravitational potential energy. So that depends on mass times gravity times height. When they said the mass of the fuel ejected is small, that means the mass basically stays the same. The height is increasing, so that means that the GPE's got to be increasing. So that gets rid of C because it says it's decreasing. And then the mechanical energy of the system. So we know that if kinetic energy increases and gravitational potential energy also increases, total mechanical energy has to increase. So that it can't stay the same. That would be impossible. So our answer is A. The second one, the figure shows the net force exerted on an object as a function of the position of the object. The object starts from rest at a position of x equals 0. It acquires a speed of 3 meters per second after traveling a distance of 0.090 meters. What is the mass of the object? So here's one that you need to know this moving forward, since we know W equals F D cosine theta, okay, or F parallel D. So basically, the force times the displacement is going to be equal to the work, which means that would be the area under the graph, right? So I'm just going to find this area here. So this is area of a triangle. So I'm going to say area equals 1/2 base times height, which is 1/2 0.09 times 3. And our area is 0.135, and that's going to be in joules. So that's going to be the work. It says the object starts from rest. So let me just draw this object, by the way. So this object starts from rest, so there's no energy. And then it goes, this is at x equals 0.09 meters. Here, the speed is 3 meters per second. And so this has kinetic energy, right? K and no E. So that means this work here. So we have 0 energy plus the work equals kinetic energy at this point. So kinetic final, I'll call it. All right, so if the kinetic energy equals the work, we've got kinetic energy equals 0.135. That comes from over here. That's equal to 1/2 the mass times the velocity squared. Velocity is 3 squared. So let's see, 3 squared is 9. 9 times 1/2 is 4.5. So we just need to divide by 4.5. And we get that the mass is equal to 0.03, and that's kilograms. Next one. Okay, so for this one, I put the correct answer on here. I don't know why. Okay, so it says an experiment is conducted such that an applied force is exerted on a 5 kilogram object as it travels across a horizontal surface in which frictional forces are not negligible. What that means is there's an applied force, let's call it a push. So I'm pushing a 5 kilogram object, probably a box, across a floor. There's also friction on it. This is a graph of the net force on the object as a function of the object's distance traveled is shown. Well, that's not true because it says it's applied force. I think they screwed this question up, if I'm being honest, because it clearly says a graph of the net force is shown. And that's not what it did. But anyway, okay, so they screwed up. But really the answer is D, because there's not enough information. Where they're going with this, let's say this is a graph of applied force, like it should have. If it said what it should have in the, then we would know that it's not enough information, because we can't figure out net work done on the object if we only have information about the applied force. The network, let's get rid of this explanation. The network W net would be equal to W friction plus W, I'm going to put A for applied. And this graph up there would only give us work applied. It wouldn't give us work of friction. So that's why it's D. It's not enough information because this only gives us one of the forces and not all the forces. All right, the graph of the net force. Which expression represents a change in kinetic energy? Okay, so first of all, we've got force versus position. So work equals FD, which just means area under the graph. So I'm going to just go like this. Break it up for myself. So this is going to be force times D. So this is FD. This is going to be 2D times force. So 2FD. So that bottom is 3FD. Oh, I didn't need to break it up into two different, did I? Whatever. This goes from 2D to 3D. So that's D. F to 2F, that's F. So this is also FD. And this is F and D, but it's a triangle. Sorry, D and F. So this is going to be 1/2 FD. All together, FD, FD, 2FD, and a half FD gives me 4FD, 4.5 FD. Actually, 4.5 FD. Okay. That's it. Yeah, that's the change in kinetic energy of the object is going to be that, because it goes a horizontal distance, so we know its GP doesn't change. Okay, next is an example of a really wordy problem. Student conducts an experiment about mechanical energy of a block spring system. That's good. We've got this block. It's 2 kilograms. It's on a horizontal surface. Wonderful. That means we don't have to deal with GPE. We love that. It has a spring constant of 100 newtons per meter, as shown. We get to ignore friction, and then the spring is on a wall. And it's right in the block spring is initially at the spring's equilibrium. So right here, this is equilibrium. This block does not have any energy. It's not moving. It doesn't have GPE. It doesn't have EP. So based on the data collected from the experiment, the student creates the graph. It shows the force exerted on the spring as a function of the distance the spring is compressed. So if we compress it a certain amount, this is how much force we have to use, right? So how can the student use the data to experimentally determine the work done on the spring by the block? So this is the force exerted by the spring, and the distance the spring is compressed. So we want to use, specifically, it just says the work done on the spring by the block. So we can find work equals F parallel D, which just means since we have force and distance, this would be the area. Great. So determine the slope of the line of best fit. No. Determine the area. Fantastic. Bound by the line of best fit through the data on the horizontal axis from 0 to 1. That sounds good. Use the maximum value of force exerted on the spring and multiply that value by the maximum distance. Nope, wrong. That wouldn't be it, because you would just basically be doing 100 times 1, but that wouldn't make sense. Graph cannot be used. That's not true either. So it's B. Okay, here we go. An object is moving in the positive x direction while a net force directed along the x-axis is exerted on the object. The figure shows the force as a function of position. What is the net work done on the object over the distance shown? So again, we're just finding the area. Don't forget, this is the area you should be finding, my friends. Don't trick yourselves into thinking it's anything different. If you're looking at this, you can tell that this and this are the same, like they just cancel each other out. One of them, this would be positive, and this one is negative. They're both triangles that have a height of F naught, and they have a base of D. So these cancel out. So really it just is left up to this blue square here, which is a height of F naught and then a base of D. So it's F naught D. That's the answer. A block of mass 10 kilograms moves from position A to position B, shown in the figure above. Great. So the speed of the block is 10 meters per second at A and 4 meters per second at B. Did I say V? B. The work done by friction on the block as it moves from A to B is most nearly. So let's analyze what kind of energy this has. We've got kinetic energy at point A, and then at point B, we've got gravitational potential energy and kinetic. So I'm going to say that the energy at point 1 plus the work done by friction is going to be equal to the energy at point 2. So we've got 1/2 mass times speed squared, velocity squared, plus the work done by friction. It's equal to UG. So MGH 10 times 10 times 2 plus, there's the 2, 1/2 mass 10 times velocity squared. Okay. These numbers here, 3, 4, 2, they don't mean anything. What they probably will mean is part 2 of this. Once we figure out what the work done is by gravity, we could look at the displacement of 9 and figure out what the force of gravity is, but we don't care about that here. So over here, 1/2 times 10 times 10 squared. 10 squared is 100, times 10 is 1,000, divided by 2 is 500, plus work of friction is equal to 100 times 2, 200, plus 4 squared is 16, half of that is 8, 8 times 10 is 80. 500 plus work of friction equals 280. Work of friction has to be negative 220 joules. That was like the longest oven timer about my rice being done ever. All right, my rice might be done, but my main dish is not. Don't worry, I paused you guys so I could take the rice off. Okay, the student wants to approximate the amount of work that the force due to gravity does on the student as the student walks up a set of stairs. Which of the following measurements must the student collect in order to approximate the amount of work done by the earth on the student? Select 2 answers. So work done by gravity is going to equal the force of gravity times displacement. Okay, that's it. I don't know if we've gotten there yet, but the force of gravity is dependent on, I don't know if you guys got this in one of your videos. The force of gravity is equal to mass times G. G is 10. We've known that for a while. So anyway, so we definitely need the mass of the student. Yep, select 2 answers, by the way. We do not need an angle. We need the mass. We know gravity is 10, and we need the displacement. So we don't need the angle. We don't need the total length of the stairs. What we need is the final vertical height above the initial position, because that's going to give us our displacement. So we need A and D. Okay, I'm pausing this here.